is the equation for a circle, centered at the origin with radius 5. That graph right there is not the graph of a function. So what about this rule? How can we interpret this rule in terms of these graphs? What can we do? Vertical line test, okay? So you've given me a definition of something. What does the vertical line test say?
That each point on x is only one y value each.
Okay, so in interpreting the vertical line test, one way of interpreting it is that any vertical line that I draw is going to intersect my graph exactly one time. Okay? That's how we interpret this rule in terms of the graphs that we're given. Right? If you notice with these graphs, the three that are functions here, any vertical line I draw, or sorry, any vertical line, there you go, any vertical line that I draw along any of these graphs only intersects the picture of the graph one time. And that's in at most one time. There may be some vertical lines that never intersect our graph, but each one of these graphs does in fact pass that vertical line test. Okay? The circle picture there obviously does not, which again is indicative of why it's not a function. Okay? So, two different ways right now that we can interpret graphs. We have functions and we have pictures. Other ways we can interpret graphs, or other ways that we can represent functions. Other ways, we can always draw little tables of data. We can use tables to represent functions. Typical table looks something like this. X values in one column, function values in the other. Let's see. Is this table an example of a function? Does this table represent a function? In interpreting this as a function or not, what do we have to check? What do we need to check to make sure that this is in fact a function? Okay. What we have to do is we have to make sure that each input has exactly one output. In other words, we look at this first column, we look at all these input values, and we say, does any input value show up more than once? Well, in this case, no. All of the input values are unique. There's only 4 input values, none of them are repeated, so this would in fact be representative of a function. If I was to put another value in, put a -2 down at the bottom, does this now represent a function? Okay, this now has the same value repeated 2 times, and there are different output values, there are different f of x values that go along with that same value, so this would not be representative of a function. Okay? All right, now, in reality, we're going to use all 3 of these different representations of functions at some point in time. Typically, what we're going to do is we're going to start with a rule. We're going to start with our equation of a function. We're then typically going to find a table of values, and ideally then, we're going to use that table of values to identify what a graph looks like. Okay. For many of you, you've probably identified what a lot of functions graphs look like. You probably know what the graph of x squared looks like off the top of your head. You may know what the graph of 1 over x looks like off the top of your head. But if I start putting up slightly more complicated functions, you may not have a good understanding of what that picture looks like. Being able to identify how to find these tables of values and then use that to find a graph is going to become helpful. And for those of you that have graphing calculators, you can just, in your graphing calculator, fix that. We'll see that being able to identify functions in all 3 different ways is a useful skill. that we really want to pay attention to. All right, now, so far what we've done is we've looked at functions in these three different ways. What I've done is I've sort of glossed over a little bit of language that is important when we're talking about functions. Functions take inputs, and for each input, give you a unique output value. Okay? Everything we've looked at so far have been functions of x. Okay? A function of x is a function whose inputs are the x values. Okay? Pretty straightforward idea. Nothing really tricky there. But not all functions are functions of x. What do I mean by that? Well, let's take a look at the following table. All right, so here we have a table of data values, x's and y's. Go down the x column, you look and you see that there are some values that are repeated. So the first question we can ask is y a function of x? In other words, is y equal to some f of x? Can I find some function out there, or can I interpret y in some way that y is a function that depends upon the input values from x? Is this table right here a function of x? Back to our rule, back to our definition. Is it a function? Why not? Right, there you go. Okay. So there are multiple inputs that are repeated, multiple x values that are repeated, but their y values are different. Right? Okay. So the -3 shows up twice. In fact, the +1 shows up twice too with different y values. Okay. So in this case, y is not a function of x. All right. Well, let's turn the question around then the other way. Is x a function of y? If instead of using the x values as my inputs, I use my y values as my inputs, does this table represent a function? Does each y value have a unique output value? Sure. 2 goes to -3. 1 goes to -5. Does 2 and 1 ever show up on the right-hand column again? No, they don't. In fact, none of the values on the right-hand column are repeated. So yes, this table can in fact be interpreted as x being a function of y. So when looking at tables of data, when looking at expressions or formulas, equations, whatever you want to call them, when looking at those, you might not have a function from one to the other. You might not have y equals f of x. It might be the other way around. Again, what I want to get at is that the input values, the letters for the input values are not relevant. The letters you choose for your inputs are irrelevant. You can choose any letter you want. What you're looking for is you're looking to see, can I find a way of relating each input to a unique output? And if you can, then however you've identified that relationship gives you a function. I don't know of a formula that would, give me this output table, but there is some sort of function that relates y's and x's in this case. All right. Now, what we want to do now is talk a little bit more about how functions behave in relation to these inputs and outputs. So, the inputs of a function are given a name. The set of all inputs is what is called the domain.